So we have talked about the first of the processes, short-term breakdown processes, that is your intrinsic breakdown. Next we come to what is called the avalanche breakdown or the streamer breakdown. In this, we are postulating that a process very similar to the streamer mechanism in gases can be responsible for breakdown in solids as well. So you have an electron which acquires enough energy from whatever may be external field or temperature, and it enters into the conduction band. So it has enough energy to become a free electron. Once it becomes a free electron, if you have sufficient number of free electrons, these free electrons will be accelerated towards the cathode by the external applied fields. Normally, in a solid, the mean free path of an electron is so small that it cannot acquire enough energy from the field so that when it collides, it can cause ionization. However, theoretically, it is possible that the free path is long enough for the energy gained by the electron between two collisions to exceed the lattice ionization energy. Here, what we need is the lattice in a solid. What energy we need is lattice ionization energy, so that when the electron strikes a particle, that particle will have to overcome the lattice binding energy and come out as a free electron. So let us imagine, theoretically, it is possible that the mean free path is long enough for lattice ionization energy to be gained by the colliding electron, and an additional electron is produced. So you continuously need to have these collisional processes in a large number of collisions, and as a result you have an electron avalanche being created in a manner very similar to gases, and this avalanche leads to breakdown. Now you can well imagine that this is very unlikely and require very large energy. So again, this is not a process which you commonly encounter in practice. The third short-term process is the electromechanical breakdown. And if you note the term electromechanical, so it's a mechanical breakdown that we are talking about. So when I say mechanical breakdown, I mean that I have a dielectric material. It's a solid material and it mechanically breaks. So there is a fracture of the material, or maybe there is a crack formation in the material, a discontinuity, a material discontinuity is formed. What has electric stress got to do with it? Let us imagine I have a solid material and I apply an electric field. So when I apply an electric field across this material, there would be, let's say there are some surface charges here and surface charges here, because I've applied an electric field. So I put the charges here, and the charges are not allowed to move into the dielectric volume because it's a dielectric. So you have positive charges here, you have negative charges here. And these opposite charges should attract each other. So as a result, across the volume of the dielectric, these charges will attract each other. As a result, there will be compression forces. So because of the electrostatic attraction between surface charges on two opposite surfaces, there will be compression forces which will try to kind of compress the material. If the material is such that it is able to deform appreciably without fracture, so there might be two outcomes. Because of the compressive forces and the material is not able to deform, it can break. There might be a collapse, so the material might just simply collapse because the test specimen experiences forces which are greater than its mechanical compressive strength. So the compressive strength is so high that it just mechanically fractures. Or it could be that if the material deforms, let us say it has some ability to deform. Now when it deforms, the opposite surfaces come closer to each other. When they come closer to each other, they attract even more. When they attract even more, the compression forces are even higher. So basically what is happening is, due to the attractive forces between the two opposite surface charges, the material may suffer very high compressive forces which can cause the mechanical to mechanically rupture, which is why it is called electromechanical breakdown. The cause is electrical or electrostatic, but the breakdown is mechanical in nature. If your material breaks, it doesn't matter your insulation. Even if it has not lost its insulating property, it's not going to be useful to you as an insulation. The pressure exerted, to give you an idea about the kind of pressures we are talking about, let's say you have a filt of 10 to the power 6 volts per centimeter applied. In that case, the mechanical pressure can be as high as several kilonewton per meter square. So it's not a nominal value. And over and above that, if you have irregularities, any kinds of deformities, there will be stress concentration. So this, what we have talked about is, we are talking about an uniform field. Now, over and above an uniform field, if you have irregularities, material irregularities, there will be stress concentration, and in the region of stress concentration, the compressive forces may be higher. The situation may be exacerbated due to stress concentration at irregularities. This stress will depend upon the Young's modulus. The Young's modulus may change with time, may change with stress, and as a result, electromechanical breakdown might occur. So these are the three most short-term, the processes which take the shortest time. So if your material breaks down immediately, it is possible that these processes might be happening, provided you have very high energy levels. But the most likely situation that you would have, especially in power apparatus and system, is thermal breakdown. That means heat is the cause of the energy. Now, let's say you have applied an electric stress on an insulation. A dielectric material is supposed to have zero conductivity, but we know that no material has zero conductivity, and there is a finite DC conductivity. Remember our first slides. So there is a finite DC conductivity. Every material has a finite DC conductivity. So a current begins to flow. And because of this conduction current, as well as dielectric losses due to polarization. What do I mean by dielectric losses due to polarization? Let's just let me take the simplest case. When a material polarizes, the dipoles are created, and the dipoles tend to align themselves in the direction of the field, which means the dipoles are rotating. They are not free to move from one point to another, but they are free to rotate. So there is some movement, some confined movement, but movement. And movement of charges is equivalent to current. Whenever there is current, there is heat loss. So that means in a dielectric, when you apply an electric field, heat is continuously generated due to conduction currents and dielectric losses due to polarization. Now, once heat is generated, the temperature of the material increases. When the temperature of the material increases, conductivity of the material increases. So as temperature increases and conductivity increases, temperature increases, there might be a situation where a condition of instability is reached and the material gets much too heated, and probably often enough when we expect that there will be heating, there are also processes for cooling the insulation. In a transformer, you have transformer oil. In air, you have air. So there is a cooling going on as well. Now, there may come a time when the rate of heating exceeds the rate of cooling. And if that happens, then you will reach an unstable situation. As a result, the material may undergo thermal breakdown. So here, if you see, you have three plots. The dashed curve gives you the the heat lost versus temperature. It's increasing with temperature. And then you have three plots. This is when you apply a particular field. Here also there is heat gain, but the heat gain is always lower than the cooling law. So you effectively you do not have overheating. Some heat is gained, more heat is lost. In field 3, you have a situation where the heat gained is too much faster, the rate of heating is much higher than the rate of cooling, and as a result, this scenario can give rise to breakdown. Whereas in this field 2, you might be able to work at a scenario, for example, if you work at temperature T2, you have a situation where heat gain is equal to heat loss, and you have an optimal situation. So you can also work with this field 1, And if you're working with field 1, you will be able to operate at a much lower temperature. Whereas maybe with field 2, you will be able to operate at a higher temperature. So this is the characteristic of the material. So most of the time you will find that in power systems, power apparatus, you find that whenever an insulator fails, insulating material fails, when you go and see what has happened, most of the time it has failed thermally because of overheating, and we have to make sure that thermal breakdowns can be controlled.